Hello everyone, welcome back to our NDT training session. I am Muthulakshmi Kanagaraj, Quality Expert, ASNT Level 3 in 10 methods and API, PMP and Frusio Level 3 certification holder. Now we are discussing about magnetic field theory, which is the foundation for understanding magnetic testing and magnetic particle testing. We will learn how magnetic fields and domains and source of magnetism works, as they are crucial for performing accurate magnetic testing inspections. Let's start our session. Let's start with magnetic domains, which are the microscopic regions in ferromagnetic materials, where atomic magnetic moments align in the same direction. Atomic magnetic moments aligns. Imagine a material that can be magnetized. Inside it has tiny and inherent magnetic regions. This is called magnetic domains. It has two directions, that means poles. In unmagnetized state, domains are randomly oriented, cancelling each other out. This is called a zero net magnetism. Now, if you introduce an external magnetic field, it's like a drill sergeant arriving. These domains then start to align themselves with the applied field. So it can be aligned. Same. When they align, the material suddenly behaves as a magnet. It's like a magnetic domain is like a miniature magnet. Each one of these little domains, by the way, has its own positive and negative ends, just like tiny poles. This concept is a key for magnetic testing because flux leakage and particle attraction depend on how domains align with applied magnetism. Next, let's discuss magnetic poles and lines of force, which describe how magnetic energy behaves. Magnetic force is strongest at the poles. The localized poles are north and south ends. The magnetic lines of force always a closed loop. Imagine this is a magnet. Magnetic fields or lines of force are always closed lines. Do not cross each other. Travel north to south outside the magnet. They never just start and stop randomly. They do not cross each other. Outside the magnet, they are considered to flow from north to south pole, and inside the magnet, they flow from south pole to north pole to complete the loop. These lines are weakened with distance from the poles. The magnetic field strength is based on the number of magnetic lines of force. A magnetic bar develops a total force equal to the sum of all its magnetic domains. The magnetic force is proportional to the number of lines. If there are only 4 lines, then the force is weak. If there are 10 lines, the force is very strong. So the force is based on the number of flux lines. If the magnet is broken, then each piece will form its own north and south poles. And remember, unlike the poles attract like poles repels. That means opposite poles always attracts. Let's move on the next slide. Types of magnetic materials. Understanding the types of magnetic material is crucial in magnetic particle testing because not all materials respond to the magnetic field in the same way. We classify them into three main types based on their permeability. So, permeability means ability of a material to allow magnetic lines of force to pass through it. Just say it measures how easily a material can be magnetized. Suppose one material with high permeability, they allows magnetic flux to flow easily. So this is the permeability property. There are three main types based on their permeability. First one, diamagnetic, paramagnetic and ferromagnetic. Diamagnetic material, these have a permeability slightly less than air. When you put them in a magnetic field, they actually oppose the applied magnetic field. So they don't accept the magnetic field. Examples, mercury, gold, zinc, this is the best examples. Next, paramagnetic materials. Paramagnetic materials have a permeability slightly greater than that of air. They show a weak alignment with an external magnetic field. But this alignment typically disappears as soon as the field is removed. Exhibit very weak magnetism only in presence of an external field. Example, aluminium, platinum, wood and copper. Next, ferromagnetic materials. These are the superstar for us in MT. They have a much greater permeability than air. They shows a strong domain alignment when a field is applied, and importantly they are retentive, meaning they retain some magnetism even after the external field is removed. Whenever we remove the external field, then also they carry some magnetism after the field is removed. That is called retentivity. Some common example is iron, cobalt, nickel. These are the examples. Only ferromagnetic materials have magnetic domains and are therefore suitable for magnetic particle testing. So you won't use MPT on aluminium or brass for instance. So let's move the next video. Retentivity. Retentivity, a key term we just mentioned in retentivity. This refers to the ability of a material to retain magnetism after the external magnetic field has been removed. This property is very important for us in evaluating magnetic behavior and is directly used in MT procedures. Then, source of magnetism. Where do these magnetic fields come from? There are three primary sources. First one is permanent magnets, Earth's magnetic field and mechanically induced magnetism. First we see permanent magnets. These are created by heat treating special alloys in very strong magnetic fields. This process aligns their domains permanently. You encounter them in everyday items like DC motors, speakers, magnetos. Some well-known examples of these alloys include conifer, conico, and powerful supermagnets like neodymium, iron boron. These are the best example for permanent magnets. Earth's magnetic field. Our own Earth acts like a giant magnet with its own magnetic poles. While relatively weak, that means around 0.03 MT, the Earth's field can still induce magnetism in large moving ferromagnetic objects, such as aircraft flying through it. This is also why we sometimes need to consider the orientation east-west during the demagnetization process to counteract the Earth's influence. During demagnetization, the orientation of the part relative to the Earth's field is important. If aligned east-west, the influence is less. If aligned north-south, the path may retain slight magnetism due to field direction. When demagnetizing, sensitive parts rotate or reposition them to minimize Earth's field influence. It can reduce the effectiveness of demagnetization if the part is not properly oriented during the process. Next, mechanically induced magnetism. Magnetism can also be mechanically induced in ferromagnetic materials. Mechanical force like bending, rolling, forging, and hammering or cold working can align magnetic domains in ferromagnetic materials. This unintentional alignment creates residual magnetism in the path. When stress or deformation occurs, the atomic domains shift and align, producing a weak magnetic field. Think about bending or shaping a steel pipe. This mechanical process can induce magnetism. This type of magnetism can often be removed by demagnetization techniques. For example, using AC coils or yokes. It is also important to note that when one component gets magnetized this way, nearby ferromagnetic parts might also become magnetized, which means you might need a sequential approach to demagnetization for whole assembly. And mechanically induced magnetism can attract magnetic particles unnecessarily, it causing false indication. Affect demagnetization process, especially if multiple components are in close proximity. Lead to misinterpretation if the inspector is unaware of residual fields. In NDT, this can lead to false indications or inspection errors, so proper demagnetization is critical before and after testing. I will share some questions related to this topic. Please write your answers in the comment box so we can review and discuss them together. I hope these details helped you to understand these concepts better. We will see the next video. If you have any questions or need clarification, drop them into the comment box. Thank you.